Yeah, not the Voltaire run.
I do not care. It's fine for a while.
All right, welcome back, everyone. Welcome back. Let's continue. Our ultimate goal today is to finish chapter 20. And then we have one more chapter on thermodynamics we'll do next week. And so next Tuesday we will have a quiz covering chapter 20. And so that will be quiz 3. And then the following week we will have not a quiz, we'll have a test. Test number 1, and it will cover 4 chapters. It will cover all thermodynamics, 18, 19, 20, and 21. Okay? So that is that. The big thing we had last time was that temperature was directly related to the kinetic energy of the individual molecules or atoms that were moving in a container or in a system, right? And we're going to continue along that, and we're going to talk about heat, how heat transfers between microscopically, and why it transfers from hot to cold, and then we will talk about the second law of thermodynamics, and that will be the end of this chapter. Chapter 21 is applications of all this stuff. Okay. Your quiz will be handed back at the end of class for the section that will meet with me later. I will give you back the quiz during class there, but just to fasten the process. But for the section that won't meet with me until next week, you will get your quiz at the end of this. Okay? All right. So to start this, we will start with take a container. It's insulated, isolated from the world, and it has some gases. Let's say they are monatomic for simplicity. Okay? And there is a little barrier here. The barrier is just to keep the molecules of one gas on this side and the other one on this side, but they can still collide between each other. The molecules can still collide. So, for example, here is system 1, and it has n atoms. Let's call it N1, and they are at temperature T1 or T1 initially. And then here is system 2, and 2, and it's at some temperature T2. So there are molecules moving around. If you like, so here are some molecules from system 2, and they're moving around. I drew them in blue, and these I will draw them in orange. What do you think? Which ones are moving faster? Which one is hotter?
The orange one.
Yeah, the orange. Yeah, basically that's my color coding. So that means T1 initial is larger than T2 initial. So on average, these molecules here, they have more kinetic energy than these, right? On average. It doesn't mean that every one of these has more kinetic energy than every one of these, because remember, it's a distribution. Okay. So the question is, what happens? So they can collide through the curtain here. The analogy of the book was, it's like a shower curtain, and you have basketballs or baseballs, and they're colliding through the shower curtain. The curtain basically has no normal force on them, so they can collide freely. Okay, it's just to keep them separate. And so what happens? So if you have a fast molecule here colliding with a slower moving molecule here, what usually happens on average? Which one will?
The slower becomes faster, and the faster.
Slower becomes faster, and the faster slows down a little bit, right? So at the end, eventually, after you let them settle down, they will all have, on average, about the same kinetic energy. Okay? So the question is, what is the total energy at the beginning, and what's the total energy at the end? And then we can look at how much heat is transferred between them, right? So let's look at E1 initial. The total energy of molecules number 1 how is it related to their kinetic energies and so on? Or how is it related to their temperatures?
NCB delta T.
NCB delta T, yep. And so it would be, in terms of the number of molecules, since I have
that's right.
capital N, it was, remember, 3/2? Per molecule is 3/2 KB times T, right?
Oh, that's right, yeah.
For each one. But I have N of them, or N1 of them, so that's N1. And then for system 2, you got the total energy. So if you add every molecule, its kinetic energy, you would have E2 initial would be 3/2 N2 KB times the temperature, right? Oh, I should say T1 initial. T1 initial. And this one is T2 initial, right? They start at two different temperatures. So what's the total energy for both systems combined? E total will be, you add them, right? Okay. You add the two energies. So it would be E1 initial plus E2. Now, after you let them collide and collide and collide, they would come to thermal equilibrium. Now, this total energy, is it constant or does it change? It is constant, yeah. And the reason is the system is isolated, so there is no heat that flows from the outside environment into the two systems. The two systems can exchange energy between each other, but for their total energy is constant. There is no work done on them from outside, and so there is their energy here will be constant. Their total energy is constant. Now, after they settle down, the final energy will be the same, right? T1 final will equal to T2 T2 final. Right? Their total energy will be the same. So once they settle down, will they have the same energy? Will they have the same temperature? How much energy is contained in system 1, and how much energy is contained in system 2? In other words, what is E1 final versus E2 final? How is it? Yeah. Is my question clear?
Yes.
How do you know the total energy is the same?
Yeah. The total. How do I know this is the same?
Yes, yeah.
Right? Yeah. So the energy is the same. The energy, remember, it's the heat that you put in plus the work, right? So this this system here is insulated and isolated from the whole world. So there is no work done on our system, and there is no heat that enters or leaves our system. So it is it's constant. So that's how I know. So so at the end, how much energy will be in system 1 and how much energy will be in system 2? Their total will still be the same, but how much is on either side? Which system will have more energy? The one with more molecules or less?
More.
Yeah, the one that has more molecules. Let's say every molecule at the end will have 1 joule of energy. They will have much less, but let's say every molecule has 1 joule of energy. We started, let's say, with 20 molecules here, but we had 80 molecules here. So these would have more energy at the end. I feel like there is a gap between what I'm saying and the understanding. Is it clear? Yeah. Oh, it's so, okay, so it's obvious. Okay, then I'll continue. All right, I just couldn't figure out whether it's just so obvious that, you know, my question is boring or.
We're just
Okay. So the energy at the end will be this. You take the. Yeah.
Is the system one, is it mixed?
another.
There is a curtain between them, so the number of molecules on the left will always stay the same, and the number of molecules on the right will be the same. And this thin curtain here will allow them to collide. Initially, the temperature is different. At the end, it will be the same temperature. They will settle down. Yes?
Is N the same in both of the systems?
And?
Yeah.
No, it's a different.
So both N is different and the temperature is different?
Yeah, initially the temperature is different and the number of molecules is different.
Okay.
Yes. I will do an example actually with numbers soon. So maybe that will, yeah.
How do you know if that's monatomic or diatomic?
I'm assuming it's monotone
Oh,
for now.
for
Yeah.
So would your E initial, E1 final would be like the sum of those two averaged?
Let's see.
Okay.
So, in a way, yeah, it's some sort of an average. So it will look like this. The number of molecules in system 1 divided by the total number of molecules times E total. If 50% of the molecules are, or if 80% of the molecules are in system 1, then system 1 would have 80% of the energy. So for this system here, it would have N2 divided by N1 plus N2 times E2. You can write it in number of moles also. You can say, you can write it this way. N1, 1 plus N2, E total. This one is 2 over N1 plus N2. Total. Yeah, looks good. Yeah. So now, let's see how much heat is transferred to system 2 and how much heat is lost by system 1. Okay. So, no heat flows from the environment, from the outside, but the two systems can exchange energy. In fact, the hotter system will lose energy to the cooler one. Okay. But the total energy will be the same. Okay. So, here. So how do I get delta E for system 1? What's the change in total energy for system 1?
E2 minus E.
Yeah, the final minus the initial. It's E1 final minus E1 initial. That's minus E1 initial. And how is this related to the heat? First one. How is the change in energy for system 1 related to the heat lost or gained by system 1? It's equal to the heat. Yeah. Why?
There's no work.
There's no work done.
Oh,
Yeah.
okay.
Yeah. So this is equal to the heat I should have allowed some space for myself. It's equal to Q1. It's called Q1. So let's write it down. So you have E1 final, that's E1 final, minus E1 initial. That's the change. So, right, this is E1 final. It's this. What I'm trying to show you is that the heat lost by system 1 will equal to the heat gained by system 2. And that's how heat transfers. That's it. Yeah. So you have E1 final is, you can say N1 over N1 plus N2 times E total minus E1 initial. And then Q2 is delta E2 is equal to E2 final minus E2 initial, and that's equal to N2 over N1 plus N2. E total E2 initial. Okay, so the final part on this, I want to show you that Q2 is equal in magnitude to Q1, but it will have a negative sign. They're just negative of each other. Okay. How would I show that? It's actually not that difficult. You can say, all right, so it's clear. So I want to show that Q2 and Q1 are equal to each other in magnitude. One of them is the negative of the other. If Q1 is the heat lost by this one, it has to equal to the heat gained by this. So how do I show that? By direct substitution. So I say, all right, here's Q2. It's equal to this, N2 over N1 plus N2 times E total minus E2 initial. How is E2 initial related to E1 initial? E2 initial is equal to what? Start here. E2 initial is equal to E total minus E1 initial. I'm going to substitute that. And then it will involve a little bit of algebra. Actually, very little algebra. And then we will be done. It's equal to E total minus E1 initial. Okay. And let's combine these two. So we have Q2. So you have N2 over N1 plus N2 times E total, and then minus E total, and then minus becomes plus E1 initial. So I have something times E total minus E total. So if I factor out E total, I would have what? I have E total. I'm just trying to combine them in one step here. So I have N2 over N1 plus N2 minus 1, right? I'm combining this times E total minus E total. If you factor E total, you would have negative 1 here and this. And then here minus becomes a plus E1 initial. What is this? If you do N2 minus N1, N2 divided by N1 plus N2 minus 1. You have a common denominator, what do you have? You would have, if you combine them under the same common denominator, you would have N2 minus what?
Minus N1 and 2.
Yeah, minus N1 plus N2. And so if you do that quickly, what do you get? N2 minus N1 plus N2, you get?
N1.
You get negative N1.
Negative.
Right? Because there is a minus sign. So you get negative N1 over N1 plus N2 times E total. So you get this. You can look through the algebra yourself a little bit later, but combining this will give you negative N1 over N1 plus N2. The minus sign is given here, times E total plus E1 initial. And compare these two. This one, this expression, with this expression. There is a minus sign here, but there isn't a minus sign here. And there is a plus sign here, but there is a minus sign here. So they're negatives of one another. So this one is just negative. That's all. I won't know. And so
So at equilibrium, will the temperatures of the samples be the same, or the
Yes.
temperatures of the individual molecules in the sample be the same?
So the temperature is a macroscopic reflection of the kinetic energies of the individual molecules. So on average, so their temperature will be the same for both samples, and on average, the kinetic energies of the molecules will be the same on both sides. So the kinetic energies of each of the molecules on system 1 and system 2 will be the same, and therefore their temperatures will be the same. Yeah.
I remember from the graphs, like the PD graphs, that there was no work done when it was isoporic, right?
Yeah.
So that's when Q is equal to delta E. Is this the same situation?
In here we're looking, so for the work done when you're looking macroscopically at the system. So here, yeah, we're not doing any work. We're
Okay.
not- Yeah, we're not changing the volume,
Okay.
and, yeah, so no work.
Okay, so
Yeah.
it just means it's doing that because technically it's the same volume and that's why we can set it equal to each other. Cause
Yeah.
there's no work, okay.
Yeah, so there is no work
Okay,
done.
thank you. Thank you.
And then there is no heat transferred from the outside to the inside, but the two systems, they can exchange heat between each other.
Okay, that makes sense. Thank you.
Yeah. So basically, what we're saying is, if you put a hot object next to a cold object,
Heat will transfer.
what you always knew since you're a kid, the hot object gets cooler and the cold object gets warmer, and they come to some common temperature. Never the opposite. You never have heat going from cold to hot, meaning the cold keeps getting cooler and the hot keeps getting hot. It just doesn't happen. Yeah. Okay, so let's do an example. Let's do an example to make this maybe more clear, okay? I started writing the example earlier, but I didn't finish. So here's the example. It says, you have a sealed and insulated container. So here is a container. So it's sealed and insulated, so no heat can flow from the outside, no work, nothing. And there is a barrier. And if this container contains 2 grams of helium on one side, so there is helium. And that's on one side, and it's 2 grams of helium, and I tell you that the molar mass of helium is 4 grams per mole. So how many moles of helium do we have here? Huh? If I had 1 mole, I would have 4 grams, but I have only 2 grams, so how many moles? Half a mole, okay. So now, the helium is initially at 300 K. So T1 initial, so 300 K, let's go, 300. Okay. That's the initial temperature, okay? On one side of the barrier. So there is a barrier, so that's the helium on this side, let's say. Okay? It doesn't matter which side, left or right. Now how about on the other side? On the other side, you have 10 grams of argon. So on the other side, on the other side, we have 10 grams of argon. And argon would have a molar mass of 40 grams per mole, I believe. Yeah, it is 40, I think it's 10 grams. And this argon has an initial temperature of 600 K. So argon here at an initial temperature of 600 K. At 600 K. So treat both gases as monatomic, so both of them are monatomic, so the energy would have 3/2 NKT, right? So the questions are, how much energy, how much heat energy is transferred and in what direction? How much heat is transferred? Transferred at 2 bars? Yeah, it does. And in what direction? I think we can answer the direction part. Heat will be transferred from where to where?
From the argon to helium.
From from the,
Right?
yes, from the hot to cold, yeah, or hotter to cooler. Yeah, so that's the direction, so we have answered this one already. Now, how much? So we get to that in a second. And then B, what do you think B will ask?
How
What do you
much?
wanna know?
Oh my God.
The final temperature?
Yeah, I mean, yeah, you mix them and you wanna know, find T final. So find T final. What's the final temperature of the system? So, yeah,
What do we gain knowing the container's insulated? Like,
Oh,
sealed is like, no like volume change, but like, what about insulated?
well, if it's open, let's say the environment has a temperature of 293 degrees Celsius, right, room temperature. Well, if it's in that room and it's not insulated, the final temperature every time would be 293, would be the room temperature.
Oh, I see.
Yeah,
So it's just like these temperatures that are
yeah, so meaning we're just focusing on this system of two things, yeah. Yeah,
So it's like energy is conserved, right? Oh.
yeah. So we're going to do that. In fact, so notice this, both formulas here, they involve the total energy, right? So we want to calculate the total energy, in fact. So we need the energy of the argon molecules and then the energy of the helium, or helium atoms and argon atoms. And then we will add them together. So, let's call this system 1, and here's system 2. So, E1 initial will be, I can put 3/2 NKT, but since I have the number of moles, I'll put nRT. So 3/2 N1 times R times T1 initial. Now, again, the number of moles, I think we just argued that you can put the mass over, the molar mass over, or the mass over the molar mass, and you get 0.5. So we have 0.5 moles, so N1 is 0.5. So N1 is 0.5 moles, and then the number of moles of system 2, how many moles does the argon have?
0.25.
We have, if we had 1 mole, we would have 40 grams. 40 grams for every mole.
0.25 moles?
0.25, yeah, thank you. So quarter mole, 0.2. So let's plug in the numbers. So we have 3/2 times 0.5. You remember what R was? 8.31, and then the temperature. It's 300. And I will read the number for the sake of time. 1870. 1,870 joules. That's how much energy is on these, for these atoms. And then E2, initial, would be 3/2, and 2, R, T2, initial, so 3/2. Argon is a quarter mole, so 0.25, 8.31, 600 for the temperature, initial for the argon. You also get 1870 joules. And the problem is constructed in such a way that the number of joules, the thermal energy of each is the same. So does it mean if they have the same energy, same total energy, heat is not transferred?
No.
No. Yeah, the energy per molecule is not the same because they have different temperatures. Yeah.
Oh.
Yeah, so let's say if you have a mass, if you have one mass that's moving at 100 meters per second, and then you have a bunch of masses on the other side, each of them moving at 1 meter per second, but you have 1,000 of them. There's more energy in the side that are moving at 1 meter per second, but on average, they're moving at 1 meter per second, whereas this one is moving at, I forget the number here, 10 per second. Okay. So they have the same energy, but heat will flow from them.
I just wanted to recap what you said. So heat is still transferred transfer because the energy of the molecule is different.
The energy per molecule.
The energy per
Yeah, is different.
Okay,
So what's the total energy? E total. Add them, right? So you got 3740. Thank you. 3740 joules. That's the total energy. So now let's calculate the final energy for molecules 1, and then the final energy for molecules 2, and then we can find what the heat transfer is. So E1 final, I would refer to this. It's the number of moles of 1 divided by the total by the number of moles of both systems times E total. And then the same thing for number 2. So let's do that. E1 final will be N1 over N1 plus N2 times E total. So you have 0.5 over 0.5 plus 0.25 times 1870. No, not 1870, right? Times what?
37.
Yeah, 3740. Total energy. Yeah, 3740. And that gives me 2493. Joules. And then E2 final is N2 over N1 plus N2 times E total. You get 0.25 over 0.5 plus 0.25 times 3740. 3740, and that gives 1247. Yeah.
Would the second one be technically negative because that's the one of argon? So that's how much. Oh wait, no, it would be like the total minus that. It would be how much it lost.
So you're one step ahead of me.
Oh,
yeah,
okay, sorry.
yeah,
I was-
which is the heat. So
Okay.
now, yeah, you're thinking that's good. So now, how much energy was lost by system 1 versus system 2? So to figure that out, because that's the ultimate question here, not the ultimate, but one of the questions. How much heat is transferred and in what direction? So the heat Q1 will equal to delta E1 for system 1. And so for system 1, the final energy is 2493, right, for system 1, 2493 at the end, but it started with 1870. That is 623 joules. Q2 is delta E2. What is E2 final? It's 1247 minus 1870, right? System 2 ended with 1247 and it started at 1870. So the difference, well, this number is less than this one, so it will be negative. And it's not surprising that it's negative 623 joules.
Because it's the same.
Yeah. So system 2 lost, system 1 gained heat. So, and then finally, what's the final temperature? Well, let's find it. I know that for system 1, the temperature, E1 final will equal to 3/2 and 1 R E1 final, right? Energy. So solve for T1 final, and you get T1 final therefore will equal to E1 final over 3/2 N1R. And E1 final is what? What was the final energy for E1? 2493, right?
Oh, we.
Right, 2493 divided by 3/2. N1 is 0.5, right? And R is 8.31. And let's do this. By the way, the temperature is expected to be between two temperatures. What should it be? Somewhere between what?
450.
300 and 600. So we should not get something more than 600 and we shouldn't get something lower than 300. Somewhere in between. And let's see what we get. Oh, wait. 400. 400. So it's 400. Okay. How about system 2 if you want to make sure? I mean, it would be 400. That's how it would be, but if you want to double check for system 2, E2 final would be E2 just like this. E2 final over 3/2 and 2 times R. E2 final was 1247 over 3/2, 0.25, and then 8.31. And it should be 400. If you want to double check, should do that. So both, they will end up with the same temperature at equilibrium.
Professor, will you always start out with this equal E1I and E2I?
No.
No?
No.
So,
Yeah, it doesn't have to. The book on purpose gave this example to demonstrate the point that sure, they have the same energy, same total thermal energy at the beginning, but nevertheless heat will still transfer. Because there are less molecules here. So, and it's biased toward the average would have been 450, right? The average temperature. If you want to just add the two temperature and divide by 2, it ended up biased toward the helium, toward the 300, right? It's 400. It ended up with 400, and because helium had more molecules, more atoms, more moles. Okay, so which gets us to the next topic. So now, so basically the author lists several processes that do not happen, right? And he talked about how the first law of thermodynamics told us that energy is conserved. You can change forms, you can have work done, or you can transfer heat from one place to another, but it's always the same. That's what it says, the first law of thermodynamics.